larger systems. That's one way to take that limit. An equivalent way to take that limit is to imagine that you are in the 18th century or the 19th century. You don't know about h bar. And so you just, it's just like, how do you define what a mass is? You say, well, I'm comparing it to some kilogram in France. Not that far away here now. Not usual for me. And then I can imagine different theories of quantum mechanics where h bar is different sizes. And so I can take the limit in that sense.
Okay. Continuous way.
Yeah.
Did anyone do an experiment like this? Did anyone observe it?
Right.
Is it just ubiquitous and I'm surrounded by this?
Right. So being able to confirm this is true is equivalent to being able to do like a macroscopic superposition experiment,
Sure.
which is just very hard.
Your statement right there contradicts the whole point of this, though. You're saying these things are everywhere. In fact, they're everywhere where you happen to have perfectly isolated rooms, which is essentially nowhere.
Good. So
saying these are everywhere is a very misleading statement, leaving out decoherence and other.
John, you're not very generous, or you're just like, I didn't like the exact way that you said it, so you must be trying to trick me. I promise I'm not trying to trick you. I just have to introduce one thing at a time. The thing that is on the very next slide. Yeah, let me answer this question first, then we'll go to this slide.
Just to trying to understand.
Yeah, please.
What might be happening. So imagine, there's this chaotic system. There's a Lyapunov exponent,
Yep.
but I'm in the room. I look at the thing and I see it there
Yep.
all the time. And so if you tell me that it's in a macroscopic superposition of some states that you started out with, I would have said that that the system is so strongly interacting that the Hilbert space that actually describes it, has. So this happens in quantum field theory all the time. Your degrees of freedom you write down get dressed quantum mechanically such that there's something very different later. And in this real theory, they're just one state that's just there.
I'm trying to think of this. I don't think this is the same thing as stress states. So I am going to talk right now about the fact that what I described was when the pendulum is completely isolated from the whole world. No photons, no vibrations, no anything. And now I'm about to talk about what happens in the real world.
Yeah, okay. So
yeah.
Maybe I'm thinking about this wrong, and so if I am, just please correct
Yeah.
me. I'm just trying to think. I'm trying to make sense of what you said, right?
Yeah.
And the idea of saying something to the effect that it's in a superposition of something being here and there at the same time, according to the Hilbert space that you wrote down in the first place, I would say that maybe that wasn't the right decomposition of the Hilbert space into states. So in a QFT, this happens all the time, right? You write down things, you have a Lagrangian, you think, oh look, it's bosons that are weakly coupled.
Yep.
The actual quantum theory is fermions, right? This happens all the time. Your thing you write down and the actual quantum mechanical degrees of freedom are very different objects,
Okay.
depending on the theory. So I'm wondering if something like that might be happening here, just because I find it really hard to. So tell me if this is just too naive on my part.
Yeah.
If I'm looking at this chaotic system, and just with my eyes, I can just see where it is.
Yes.
Right? So how could it be in a superposition of two different states?
Right. So what happens is the photons come in, they scatter off of the object, and so you go from being in a superposition of, this is like my two masses, and then this is some sort of other configuration of it, and then we have photons coming in, right? And then there's some sort of out number one plus out number two. Okay, and these are again, the different macroscopically distinct configurations of the pendulum. So this is decoherence, right? And so if you want to be observing this pendulum, this has to be happening. You can think about it as there's a continuous measurement going on, being done by the photons in the room. If you close your eyes, the measurement is still happening. It's just you don't know what the outcome of the measurement is. But it keeps going on. However, the fact that this superposition is created is not destroyed by the fact that it's being decohered. So in particular, if you asked what is the variance of various things you might calculate here, you would find that for like normal photons, they don't really affect the variance at all. So it would be spreading out, just as you would expect classically as well. You would just never be able to confirm the superposition. All of the measurements that you can easily do are basically going to be in this basis rather than a complementary basis where you'd be able to confirm the superposition. Of course, wherever our experimental techniques are able to make the complementary measurement, where we're able to actually check whether the superposition exists, it actually does exist, right? So we can create these superpositions of, I think, the world record right now are these molecules that have 10 to the 4 AMU, so like 10,000 protons and neutrons packed into a bundle, and you can create superpositions of them. And we believe, if you think quantum mechanics applies on all scales, that this is just always happening, and we're just unable to confirm it.
That's the part I still disagree with. Always happening, except that it's being decohered all the time, so it doesn't happen.
It's the fact, so the photons are now entangled with it. So it is not a superposition in just the pendulum space. It's a superposition in the pendulum plus photon space, Hilbert space.
But surely you can tell us that's exactly the kind of superposition that doesn't count because you're measuring the wrong.
Exactly. Yeah, because one single photon goes off, and I can't confirm that whole superposition. But yeah, if I had a great mirror that could like reflect the photons back so they would disentangle with the pendulum, then in principle I could. Okay, so but the superposition is still being produced in this sense. Tell me if this sense works for you. I can calculate a variance of these guys, so like a variance of position and a variance of momentum. And it will be much larger than when I start, right? And I am assuming that the way universe evolves unitarily. So we're just saying quantum mechanics always applies. And so I have unitary evolution, and then I have this variance build up. So the system has to, it cannot still be in a basically a near uncertainty limited state. It has to be spread out over the phase space.
Okay, but you could also do that as it's just being measured, and you ought to approach the classical limit and it does all the right stuff.
Absolutely. Absolutely. But people often have this picture that when you take the classical limit, things will follow a single classical trajectory. Right? But they don't. They do this. If it's a chaotic system. That's the only claim that I'm making. It's true that these are very hard to confirm. It's true that they involve all these photons. And remember, all I'm trying to say is that when we make a measurement in the lab, this is not the only time that we're supposed to get macroscopic superpositions. Right? When we make a measurement in the lab, if you're happy with quantum mechanics applying to the whole universe, you have to say that you're going into a superposition when you make a measurement in the lab, right? And all I'm saying is that lab measurements are not the only time that happens. It happens for any chaotic system.
So you take more discussion in the coffee break.
Okay.
So it's come to an end.
Okay. Oh, yep. It's going to be, yeah. So try to finish this up quickly. Okay. A generic feature seen in these models, many models, is the generation of GHZ-like correlations. So the photon case is one where it is particularly stark. So I may slip into referring to these as redundant records, but it really is a sort of type of state or a certain type of entanglement structure with respect to some intuitive notion of an intuitive tensor product structure on the Hilbert space. Okay, and so this is something that we see in many, many cases. I'm just not going to, we had a lot of good questions, and so it was spectacular, but I'm not going to be able to finish in a reasonable amount of time. So let me think about how I want to, yeah, I may just have to describe it on the board over the next 3 minutes, and then we'll have to call it. No, let's see. Let's just breeze through it. Yeah, let's just say these out. Okay. Here's what I want. I want branches that are a time-dependent orthogonal decomposition of a many-body wave function. Right? So some way of breaking up the wave function as a function of time into orthogonal parts. One thing I would want is that coherent superpositions of these branches are indistinguishable from the corresponding incoherent mixture whenever I calculate correlators of local observables. Right? So if I had some sort of way of breaking up the wave function into branches, if I define the corresponding row, which is just to take that incoherent mixture, then good branches should satisfy this, that any sort of measurement I could make by some sort of reasonable number of reasonably local operators should give me the same thing for the coherent superposition versus the incoherent mixture. So this is some things that I might want. I would also want branches to fine grain under time evolution. This in particular means the number of branches can't decrease with time, and just the interpretation of this, right, is if I take one of the branches at a given time, do a unitary time evolution applied to it, then it was a superposition of its descendants, basically. This, I think, I'm just not going to be able to describe this. But some of the things we might want out of branches are that they are the approximate eigenstates of macroscopic observables. So hydrodynamic observables. Hydrodynamic observables are going to be things like the temperature and pressure of volumes inside of fluids. This would be things like the net magnetization of many spins over a large region. And did I lose? Oh, shit. And the center of mass, position, and momentum of large objects. And of course, the outcomes of laboratory experiments. All right, we'll just say those last two slides because this will have the interesting results, and then I'll have to wrap up, unfortunately. Okay, so this I'm going to give you sort of a proto-definition. And there will be one theorem that will hopefully catch your attention as that these might be saying something useful about real-world branches. We're going to take this idea of redundancy, of this sort of GHZ-like structure, as our characteristic, one thing that we would want, a necessary characteristic for branches, and we're going to show that it is at least close to being something that's a sufficient condition, which I found to be really surprising. So first, I'm going to define a redundant set of observables at some scale L. So pick L. This is going to be a scale-dependent definition. To be a set of at least 3 observables, 2 or more, that are local to disjoint regions with this size OL. So you can think about them as, say, being contained in spheres of diameter L, if you want. Right? So this means this is the zth observable of this set. It is built out of projections that live on that region, and then it's got some sort of corresponding eigenvalues. I'm going to say this is a redundant set of observables, if I got one for each region, if they are classically correlated on the state, meaning if they obey this. So that making a measurement on one region is exactly correlated with making the same outcome, making a measurement on a different region. Okay? So this is what I mean by a redundant set of observables. A very simple case would be if you had a GHZ state, because it has at least 3, and then the 0 versus 1 observable on each one of the qubits would qualify. It can be shown that if you consider all redundant sets of observables, so now I'm using different colors here, so the red ones would have been one observable, like some sort of GHZ information, the green ones would be another. The set of all redundant observables at the same scale necessarily commute on the state. It should say on the state. Okay. This is like I think, a non-trivial fact. And so therefore, what you can do is then you can define branches at scale L to be the simultaneous eigenstates of these observables. So it is a coherent notion to say, consider the decomposition of the wave function into things that are eigenstates of all observables copied at least 17 times. Okay? And this is a statement that you can make that sort of retains all of the symmetries of the lattice that you're on. So unfortunately, I'm out of time. I'm going to have to leave it there, but we'll talk about it at a coffee break. Sorry for not ending in an elegant manner, but thanks very much.